Okay, so the first thing I want to say is simply that, or address some of the errors that you had in your flip grids. The vast majority of your flip grids were really good, or almost really good, and had most, if not all, of the major points. Some of the bigger errors were talking about balloon getting sucked in, and since suction does not exist, that can't be right. Some of you implied that reduced water vapor on the inside pulled the sides in or pulled the balloon in. And some of you failed to talk about any collisions slash forces outside of the flask or jug. Without those collisions or forces, none of this would happen. We'd get no balloon in the flask or no crushed jug. Okay, let's get to how this all works. Okay, hey everybody. This is my response to the balloon in the flask. It is really the same as if I had made a response to the crushed jug. I'll explain the similarities and differences here and there. Okay, let's just go through the balloon in the flask and then we'll see how that relates to the jug in the flask. Air particles are red, water particles are blue. This is before putting on the heat. We have air inside and on outside, and liquid water at the bottom. We're now going to put on the heat, and as the water heats up, water becomes vapor, and its direction is all over the place, but there is a net direction of gaseous water since it's all coming from the same source at the bottom of the flask, which means as the gas is evolving, it has a net direction of going up. That is important because that means it's going to be constantly colliding with air particles. And as it collides with those air particles, because it has a net upward direction, the collision results in pushing out the air particles. In other words, the net direction of the air particles from those collisions is up. So the air particles go out of the flask as the water vapor particles collide with them. Water continuously becomes vapor due to boiling, pushing out air particles more and more. Eventually, most air particles get pushed out by the water vapor moving upward, leaving water as the primary gas in the flask. And it would be difficult to get rid of all of the air. We can assume that there is some air in there. And this was shown in the video actually by the fact that the balloon did not get inflated all the way into the flask. If you go and look at the video, the balloon stopped a couple of centimeters from the bottom of the flask, and that's because of the air that was left in there. So now the balloon is put on. We wait to put on the balloon until enough time has passed where we can assume most of the air is out of the flask. Okay, so now then we put on the balloon. The balloon now seals the system, the flask. Once the heat is removed, any hot water vapor will fill the balloon and inflate it for a little bit. So that's the inflating with water vapor particles. But on the outside of the balloon, there are constantly air particles hitting and putting a force on the outside of the balloon. And so air particles hitting the balloon, water begins to cool. So there's less water as inside the balloon. As the water cools, it's going to start condensing, and air particles continue to collide with and push on balloon. Up here, water particles in flask cool, condense, and reduce collisions inside balloon. Air particles continue to collide with and push on balloon. Water particles in flask cool, condense, and reduce collisions with balloon inside of flask. Less and less collisions up here on the balloon. More and more collisions with air in the inside of the balloon. I guess we can call that the inside of the, yeah. Well, it used to be the outside of the balloon. It's now the inside of the balloon. And that just continues. Air particles continue to collide with and push and balloon. The opposing force provided by the water vapor rapidly reduces as water particles cool, slow down, and condense. So as water vapor particles slowly cool, the inside and outside pressure remain virtually equal, not exactly equal, but almost equal. And so as the pressure on the inside decreases, the balloon will expand to more or less meet that lowering inside pressure. And so that expands the balloon, and that just keeps happening. And then here I've left a little air to show that the balloon does not go all the way down to the bottom because of whatever air is left that was originally inside the flask. So here's the balloon in the flask. Question: why is it important to remove the air particles from the flask before putting on the balloon? Okay, so let's see how this relates to the water jug. I'm going to go back to the point of putting on the balloon. This is the same as putting on the cap on. Once the water vapor has pushed out most of the air from inside the plastic jug, and so we're just going to assume that this glass flask has now turned into a plastic jug and that this is a rigid cap. So the biggest difference is, well, of course, this is flexible now instead of rigid, and the cap is rigid instead of flexible. So really we have basically the same forces at work. As the water cools down, the collisions of air on the outside of this flexible container push in the sides as there are less and less water particles on the inside due to cooling and condensing. That greatly reduces the amount of collisions, gaseous collisions on the inside, and so air particles on the outside, constant air pressure on the outside will push in that flexible material, that plastic,